talking about evapotranspiration, how to find out that. Let me it is not sharing. That something wrong in my account. I am coming just in just 1 minute. Relog in the system. I hope this will work now. Yeah, it is working. Okay, can you see my slide? Sorry for disturbance. Can you see my slides?
Sir, it is showing blank only.
Blank only. Why it is blank?
Yes, sir. Now it is visible. Yes, sir.
It is gone. Okay. Now?
Sir, just a minute. Sir, yes, sir. It is visible now.
Connection is very weak. Sorry.
Sir,
So now it
maybe
is
you can
visible?
off your video so that you can save net.
I cannot. Reason being, if I off my video, it will not be good idea for teaching. At least.
Okay, sir. Okay.
I also suppose that everybody should on and I can see that, but at least I should not have. Okay, if it is required, then I will do that. So it is visible to you?
Yes, sir. It is visible.
Okay. So it was basic idea determination or determining or getting information about evapotranspiration. And there are two methods basically. Either we can measure it, evapotranspiration, either we can measure it, that is direct measurement, or we can find out from different conditions. Or maybe climatic data. Idea. And here is the methods calculating like temperature-based methods, radiation, evaporation itself it is calculated, and combination of these methods by different research organizations it was developed. One possibility, it means one condition, that what are different methods information, so we can measure it, we can calculate. These two aspects, again we are dividing out better idea acquired, or how can be the knowledge about ET we can get. So it's important, not all, but some of the methods I am listing here. So important ET determination, estimation. Determination means we can measure directly. Estimation means we are calculating simply from the conditions or consequences or atmospheric properties or some other property. So it's, if it is a measurement, we can use instrument that is called the lysimeter. So it's coming as lysimeter experiment. We can have field experiment. We can have a field plot to measure the evapotranspiration. Evaporation and transpiration that is lost means water in the atmosphere. That is simply use of water by the crop. So we can measure by using lysimeter. We can using by experimental field crop plot, or the area where we are simply experimenting to find out it. Here is moisture study, because in this process moisture is lost either in evaporation or in transpiration. Third is, if we know the balance of the water which is applied into the field. So, and fourth is soil moisture depletion from the area. So four methods, or these are the methods in which we are simply measuring the evapotranspiration from the area. Second aspect is energy valence approach. We can use energy valence. How much energy is coming? So how much energy is coming? And you know that a fixed amount of energy, it is used to evaporate one, say, simply gram of water. So we can balance the energy, how much is it is coming from the sun, how much it is used in the system, that is our agricultural system, soil and crop, how it is lost in the atmosphere because of clouds, etc. So if we can balance the energy, we can find out how much is the total energy that is coming into the contact. We can find out this much amount of water has been removed or maybe removed by this energy. So we can use energy valence approach. Then if we are simply putting a kind of pan here filled with water, so water is evaporated, and it is evaporation and transpiration. Water lost from either water body, water surface or soil surface, that is evaporation. That water lost from the plant body, that is transpiration. So we can have an idea that evaporation from a water body, specific condition, and then that can be related to find out the ET, that is the total amount of water that is lost in process of evaporation and transpiration. So that is third method, that is evaporation pan method, or ET pans we can use. Fourth is climatological approach, like here we can use temperature, we can use radiation. These two information into the system, means atmospheric system, we can use to estimate the evapotranspiration. It is called the climatological approach, because climate has, that is temperature, precipitation or rainfall, speed, then solar radiation and atmospheric pressure. So these conditions are to remove water from any area, maybe this pan, maybe this field, maybe this crop, and so on. So we can use that information, simply temperature, because precipitation has not direct effect here, wind speed, solar radiation, and sometimes atmospheric pressure, and their interaction properties to find out evapotranspiration. So there are different methods. Just for an example, like Cradle method, Hans-Wade method, FAO, Food and Agricultural Organization, and scientist name is Penman-Montieth equation. Two scientists were involved there. So these are different methods or approaches to find out information about it. So either it is determination or measurement, or it is estimation from the conditions. Now, if you have clear idea how to get information about ET, why it is important to find out how much water it is used by the crop, so that we can find out what is the deficit to supply water as irrigation in the field. Now, let me give you a little detail about these methods. So, first one is direct measurement. So, first case is lysimeter. What is lysimeter? Lysimeter is a particular, say, instrument, we can say in short, which is used to measure evaporation or water loss from agricultural area made or large tank soil, but soil should be the same which is nearby in the area. See, it is having, the tank is having the same condition which is adjacent to this, where it is placed inside the soil. So this is the tank filled with the same condition which is there nearby in the area field. It has the same crop or plantation which is grown here, right? And if we are simply measuring the weight or simply weighing this whole arrangement, this tank filled the same with same kind of condition of soil layers, having the same plants or same crop, and if every day we are measuring the weight of this system, we can find out what is the loss of, say, simply in weight. So loss of in weight is simply either it is removed water from this system to the atmosphere, or it is excess and it is drainage, draining out from the system. So in real soil condition, lost into the atmosphere, that is evapotranspiration, or it laterally or maybe vertically. So if it is a lateral, then it is in the same system. But if it is going depth, we have interest. Suppose the crop roots are going up to 1 meter, and if it is going beyond 1 meter, it has no use by the crop. So it is basically the drainage. So drainage here we are measuring as a output from this particular tank. How much is the loss of water as drainage? Then it is simply transferred in any other direction from this system. So lysimeters are basically large tanks filled with soil and plant condition where crop is grown, and then weighing. It has two different types. Next we will learn it. If we have weighing at the bottom, find out change in weight, it is loss of water into the atmosphere. So what is ET? It is basically weight change of the system, change in weight, plus any addition of water. It's in weighing system, so it will account any addition or any either in drainage or drip percolation condition. It is change in weight change plus water added to the system minus any deep percolation or drainage. We have removed the water. So there are two types of lysimeters. Weighing, have weighing arrangement. We have mechanism to weight this whole system, whole tank. So one is baying type and another is non-baying type, and non-baying type are basically drainage type. So mechanism is weight type is we are weighing, we are getting precise information how much weight of this whole system has changed. We can have a kind of mass balance, how much it is drained. So we are collecting this drain, that is deep percolation. We can weight this amount of water. We know this whole system weight, and addition plus initial weight minus this drainage is simply evapotranspiration. Non-weighing condition, we assume that is fixed amount of water every day we are adding. So if this system is the same, what is the amount it has been lost, we are simply collecting, and we assume that difference in system is simply evapotranspiration. So in this case, inflow and drainage are measured in both type of condition, whether it's a non-weighing condition or it's weighing condition. In non-weighing, we simply assume that amount of water is used by the plant at any stage is same. So that same amount of water, we are simply assuming that it is evapotranspiration. In drainage type of system, that is specifically drainage, there is no weighing mechanism at the bottom. Soil moisture measurement are required to calculate the change in storage. But we can say that a fixed amount of water every day we are adding, assuming that fixed amount is ET every day. So to find out at the last whether there is any change in soil moisture, we need to take sample of the soil to find out any change in soil moisture. So it is soil moisture measurement that is required to calculate change in storage of the water. Like a tank filled with soil, matching completely same with surrounding, having same plantation which is in the field, placed in the center of the field to which crop is getting. And if we are measuring the weight of this whole system, with time we can get what is the amount of water that is lost from the area. So that is used, or lysimeters are used to measure the evaporation. So Bain type lysimeters measure like that is one. It could be say simple spring, or we, and this is the soil here, and this tank is clearly made and fitted on this weighing platform. And maybe certainly had strength in these walls, maybe made of steel or iron. But this same ring in such that it is same soil properties, same crop is placed are shown there. And this tank is placed in the center of usually center of the field, so that environment is same what the crop is getting. So this is basically lysimeter arrangement, and we have a weighing condition here to get the information any change into this lysimeter. So factors to be considered in constructing a lysimeter: heat advection through the wall is minimum here from here. So to avoid that difference between real soil and this tank walls, preferably using a circular tank. If you are making a circular tank, it has minimum area condition, you know it. So it is preferred to have a circular tank and little space between lysimeter and lysimeter walls and soil, just like here in between. irrigation, deep percolation is there, we can measure that how much amount it is lost as deep percolation to find out precise amount of evapotranspiration from the system. Careful backfilling of soil so that it is attaining the same layer property which we have in the. So these are but need to more careful. So this is the idea. But there are huge 1 meter by 1 meter by. Yeah. So you know from the bulk density per cubic meter, it could be near about 1600 kg, means 1.6 ton. And weighing mechanism, arranging everything, and if there is any chance of mistake, we need to lift the whole system and so on. So it is a kind of limitation as well to place the system precisely into the field. Precautions and limitations of lysimeters. ET data conditions within lysimeter match with conditions surrounding to the lysimeter, means in real field. So simply we are mimicking or we are developing the same soil condition which is in the field in this lysimetric tank. So that precaution should be always taken care or keep this particular condition in mind. Must be large enough, this tank must be large enough to minimize boundary effect and to avoid restricting root development. Suppose you are taking just 30 centimeter tank, so crop root may go beyond this. 30 centimeter is very shallow condition. So it should be a good size, and if you are taking a small, just like why not 30 centimeter by 30 centimeter by 30 centimeter, it will restrict the growth of roots. So that must be taken care by taking a larger size of this tank. High installation cost because constructing, weighing mechanism, placing in the soil, filling back the soil property with matching field condition is basically involves high cost of its installation or development. Immobility, once it is placed, you cannot change the place. So immobility precludes their use as a routine field instrument, means it cannot be taken as a routine. You can bring and measure every time, but once it is installed, it will be in that place for whole working life. A kind of limitation. These are used primarily as research tools for checking the accuracy of other methods. So this is the primary method. Our lysimeter is primary method of establishing information about ET. What is the primary method of measuring soil moisture? Anybody? Soil moisture measurement from where? Anybody? I need to check in between. Here are you have got. You are also not here. Naveen?
Sir, it is blocked, sir. Sir. So,
Okay. I feel nobody is there.
Sir, it is freeze, sir.
Now I am teaching. Okay. So this is precaution, or we can say limitation. Second method of the evapotranspiration is by using field experimental plots. We can have a smaller area as
Sir, and cannot hear anything that you are saying.
Sir, your voice is breaking. Sir, it is breaking. Your voice is breaking.
yes. Can you hear now?
Yeah, yes, sir. Now it is okay.
Where were you? Nobody was answering. What is the basic method of soil moisture measurement?
Gravimetric method.
Gravimetric method. A gravimetric method. What do you want to say? That is gravimetric method, right?
Yes, sir.
And lysimeter is the basic method of measuring evapotranspiration. So it is used as primary research tool for checking the accuracy of any other method of estimation, right? Now, the second method after lysimeter, it is field experimental plots. Farm area or in big area or research farm or any farm, a small area, it is taken as experimental plot. It is well managed, maintained, so that it is not affected from any other condition to measure the evapotranspiration. So field experimental plots is the second method of ET measurement. So measurements of water supply to the field and changes in soil moisture content of the field plots are sometimes more reliable for computing seasonal. This is basically seasonal. Lysimeter gives you information on daily time scale. So it's a more field experimental plot is more reliable for computing seasonal water requirement than lysimeter, which do not simulate field condition. Lysimeter has certain limitation that it may have wrong information about the field. But if we are taking a part of field as experimental plot, it has actual field conditions. So seasonal water requirement is measured by using field experimental plot. So it's called the seasonal ET measurement. It requires accurate measure of water applied to the field, how much it is applied as irrigation in this area. And in that way, it is satisfactory for computing seasonal water requirement of the crop or area. It does not provide information on intermediate soil moisture condition, short-term use, like it cannot give you information about daily, but it is a seasonal. It cannot give you information about deep percolation, that is in lysimeter. And peak use rate, just like at different growth stages like germination, sowing, then germination, then plant growth, then full matured crop. So peak rate of use of water cannot be determined by this method simply because it's a seasonal. So that is a kind of limitation of field experimental plot. First it was lysimeter method, second it is field experimental plot method. In this field experimental plot method, seasonal water requirement is simply calculated as water requirement is, that is irrigation water, total water we have applied as irrigation, it is measured. Seasonal effective rainfall I told that is amount which is precipitation intercept runoff and then it is effective which is coming on the ground, that is filtered into the soil to improve the moisture condition. So that is effective rainfall here. We cannot say precisely it is infiltration, but it is filled in water, means in area sometimes, so it is something different. So means removing all the losses from the total precipitation gives you effective rainfall in terms of irrigation. So irrigation water difference in soil moisture at the beginning, in ith layer of the soil, we are simply assuming that up to root zone depth there are different soil, layer 1, layer 2, layer 3, up to the root zone depth say Z. We are assuming different layers, and for every layer we are simply trying to find out what was the beginning soil moisture content in ith layer, B for beginning, and E for ending soil moisture in that we can find out total water requirement or seasonal water requirement by the crop in that sense. So D is the total depth or Di is the depth of individual layer and Ai is apparent specific gravity of the layered soil in different layers. So it is field experimental plot method. So factor affecting effective rainfall, here it is important what are factors those are affecting effective rainfall condition. Now you know that effective rainfall in terms of irrigation is the amount of rainfall water that supplies water as the need of crop or plant, that is irrigation. So in that sense, factors affecting effective rainfall, it's a rainfall characteristic. Whether it is high intensity that has no use, it will create more discharge or runoff. So it land slope, if it is slopy land, it will go fast up this area. Land slope affects rainfall. Soil characteristics, sandy, silty or clay, those are affecting. Management practices, if it is plowed land, bare land, if it is bare land, topsoil may be sealed, so it will be fast move of water as runoff. If it is plowed, it will store water. So management practices, crop characteristics, if it is a row crop or it is random grown crop, something like that. So those affect the effective rainfall characteristics along with carry your soil moisture, what it was initial soil moisture or groundwater contribution from, from the ground in that particular area. So these are the factors affecting the effective rainfall estimate or condition in that particular area to find out the seasonal water requirement by the crop. Now the third method is now soil moisture depletion studies. In the same way, just like it was a plot, and here it is, we are taking simple soil condition, not as individual plot. So this particular method, soil moisture depletion study, employed to determine the consumptive use of irrigated field crops grown on fairly uniform soil. When the depth of groundwater is such that it is not affecting or it will not influence the soil moisture fluctuations within the root zone, or there is no contribution of groundwater in the root zone moisture condition, there we are simply taking soil moisture depletion studies to find out consumptive use by the crop in a particular season. So these studies involve measurement of soil moisture from the various depths, again different soil layers, at a number of times throughout the growing period. It was basically seasonal, one time, but here it is time assuming consumptive use values of each sampling interval. Means assuming means taking into account simply here. So seasonal consumptive use is calculated by summing up or adding up consumptive use values of each sampling interval and each layer. So a correction is made by adding PT value actuality, crop ET, transpiration PT, and ET0, that is reference ET. So remember, a correction is made by adding PET values for accelerated water loss for intervals just after irrigation and before soil moisture sampling. So these are the conditions. So this is the third method, soil moisture depletion studies, to find out the evapotranspiration and use of the crop in a particular area. So in soil moisture depletion study, consumptive use is calculated from the change in soil water content by successive, means number of samplings. So this is simply U is water use from the root zone for successive sampling or every sampling. M is basically moisture content in percentage at the time of first sampling, just one. In ith layer, so it is from 1 to n layer and first sampling, and this is the second sampling. So in between these two sampling time, just like maybe every week we are taking at different places, what is the change in soil moisture in this week time or 10 days, 5 days, whatever we are deciding, we are simply trying to find out how much moisture it has lost. So it's a second sampling. So in between two successive sampling, what is the amount of soil moisture which is lost from every layer of the soil for the total depth of this root zone, because we are adding from I is equal to 1 to n. So all layers we are taking into account and multiplied by apparent specific gravity to find out the total depth of water that has been removed from the system. So that is soil moisture depletion study to find out seasonal consumptive use of the area or by the crop. Now, the fourth method of measuring evapotranspiration, these are the methods we are talking about measurements. That is basically water balance method. We can make the water balance condition of a bigger area, say like a river basin, to find out how much amount of water it is lost from this particular area, because it has different condition, heterogeneous. It is not homogeneous condition. So it could be better to find out the average ET from the area. Simply, if we have kind of arrangement to find out the water balance, how much it was initially, how much it was added, and what are different loss conditions. So this is very important, water balance approach. You might have learned this as well in land and water resources class. So water into the system that is available is simple. The available soil moisture is simple matter of precipitation, how much it was precipitated or rainfall, how much amount we have applied as an irrigation. So these two, if we are thinking about a big system like basin, either it's precipitation or it's irrigation that is added into the system. What are the losses? It's a runoff, because it's a precipitation, so it may be runoff, that is R basically here, runoff. Then it's a deep percolation, means going beyond the system, that is deep percolation, and then there is one component that is ET. So soil moisture balance gives us an idea about soil moisture availability in a particular time frame, say for whole season. It's a simply matter of difference between conditions, total precipitation, total irrigation, total runoff that has been generated, any deep percolation, and then ET loss. So current moisture or available soil moisture will be simply sum of addition minus any extraction from the system. In that way, we can find out what is ET. ET is simply W, that is available soil moisture, plus any runoff, plus any deep percolation, minus precipitation, minus irrigation. So in this way, by water balance approach, we can find out ET for a bigger area usually, but it can be applied for a small area as well. For large basin, groundwater changes are considered here. Reason being, groundwater component as well you can add. Any change in groundwater as addition of, say, deep percolation, or any loss because of requirement of ET that is supported by the groundwater. However, main limitation of this method is collecting all these information. You can get precipitation, you can get information about irrigation, but deep percolation, runoff, and other component like say groundwater, it is very difficult. So it is important, or that is kind of limitation to collect information with reasonable accuracy. That is. So these are four methods: water balance method, soil moisture depletion study, field experiment plots or experimental plots, and lysimeter are basic methods of measurement of evapotranspiration. Lysimeters are used for a say particular specific area, field on daily basis. Field experimental plots are seasonal basis, but there are differences, some benefits, so some shortcomings as well. Then it is basically soil moisture depletion studies for longer area, and finally water balance, either a plot or big basin like area. We can find out evapotranspiration or consumptive use of water by the crop. Any query if you have? Anybody? You need to speak so that I can get information whether I am connected. Yogesh? Yeah.
No query, sir.
Okay. No query. And let us move next. So first method is, yeah.
For reference crop evapotranspiration, there is a necessary condition of surface resistance of 70 S per meter.
Yes.
So surface, what is surface resistance, sir? 70
Surface
second per meter.
resistance.
What is?
That is the unit. Basically, uh, last time in land and water resources engineering, there was one condition, that is erosion. Have you learned about erosion? There are two types of erosion: wind erosion and water erosion.
Yes, sir.
In wind erosion condition, you might have heard what is the meaning of surface resistance. Means if there is a crop, right, there is a drag force of wind, and that crop or any surface cover resist that drag force. Is not that? So
Yes.
that is measured in unit second per meter. That is indifferent. This is drag force that is resisted or against by this roughness or by the crop. So that is basically unit that is derived. Did you get the point? So that is simple measure that at least this resistance should be there to measure the reference evapotranspiration. And reference means what? This is basically vegetation that is taken as a reference. So this reference vegetation or reference crop should be grown in such a way that it offers a resistance of 70 seconds per meter to blowing wind.
Okay,
Did you
sir.
get the idea? So that is the standard condition it has been taken there. So now next methods are, this is measurements part, 4 methods. Basic method is lysimeter basically because it's easy to get a range and to find out the amount of evapotranspiration from the area. And that is taken as the basic method to correct or to calibrate any other method. So after measurements, it's basically pan. If we fill, what is ET? Loss of water from the soil surface and from the plant surface, that is transpiration. So evaporation, that is from soil, and from plant it is transpiration. So idea is simply, if we are putting a say bucket or any pot which is filled with water in the same vicinity or in the area where crop is there, the loss of water is because of the atmospheric characteristics. So here as well, in the same sense, loss of water from the soil or from the plant surface, it is basically the depends on atmospheric characteristics or property. If it atmosphere is dry, it will be more loss. If atmosphere is having high, what it is called humidity, it will be less demand of water to get saturate this atmospheric soil. So there will be less loss of water. So in that sense, this observation of ants loss of water as evaporation is simply getting connected with ET. So evaporation from the standard water surface is directly connected, or we are trying to get a connection with respect to actual ET. So here it is evaporation pans which are measuring simply evaporation in a particular area where we are interested to find out evapotranspiration, and calibrated with respect to known condition of ET to make a kind of relationship so that later of evaporation from this water body or fan is simply used to find out ET of that particular crop and area. So evapotranspiration fans are used to measure the, or to estimate the evapotranspiration. So evaporation estimation, Dalton in 1982 first time stated that evaporation is a function of the difference in the vapor pressure of water and vapor pressure of air, because air is in atmosphere. So E, that is evaporation, is simply function of these two. That is saturated vapor pressure at the temperature of water surface, and ED is the actual vapor pressure of air that is measured in height of mercury. And C is simply a constant which is function of wind velocity and atmospheric pressure. So in that way, Dalton connected evaporation rate simply from a water body or from a measured pan with respect to saturated vapor pressure condition of water surface and atmospheric air with this constant. Now, evaporation from natural surfaces such as open water, just like in lake or in pond, or it is filled everywhere flooded. So such as open water, bare soil or vegetation cover is as diffusive process by which water in the form of vapor is transferred from the underlying surface to the atmosphere. It's basically a diffusive process in which water from underlying surface, from the different layers, either from soil or even in water, is moving to the atmosphere. However, its requirement is source of heat to vaporize liquid water. Source of heat is solar energy. Presence of gradient of water vapor between the evaporating surface and the surrounding air, that is essential condition to start the evaporation. The energy required for evaporation, regardless of surface where evaporation is taking place, is simply, this is the standard, and this same condition it is used in energy balance approach as well. Calories per gram of water that is evaporated at 20 degrees Celsius. So if we can correct the temperature of the atmosphere, we can find out how it is energy requirement is changing with respect to temperature condition. We can find out in that way what is the amount of water that is lost in evaporation. And that evaporation is connected with evapotranspiration. So there are different types of evaporation pans which are used to measure first evaporation. So first, United States Bureau of Reclamation Class A pan. It has a certain dimension of 120.7 centimeter internal diameter. It has, means height, we can say, is of 25 centimeter. It is filled with water that is less than its top surface, from 5 to 7.5 centimeter from the rim, and it is placed at least, means, but not more than, but exactly 15 centimeter above the ground surface in a wooden platform, so that surface heat is least affecting this system. And there is a stirring basin to check the water level that we are interested to measure. So this US Bureau of Reclamation Class A pan evaporimeter, it is called. It's the most widely used evaporation pan. It is white painted, circular, and made of 22 gauge galvanized iron. These are the standard conditions. Water is added each day in this to bring the water level a fixed point, and we are every day measuring from fixed point how much it has reduced, and that is taken as evaporation. It is calculated by. So standard wires are taking water, some are coming. That is standard wire mesh above the fan is provided to prevent loss of water by birds and any animal. The level of water in fan is measured daily at a fixed time. suppose 8 o'clock in the morning every day, it is measured that how much amount it has lost in last 24 hours. So 8 a.m. to 8 a.m. or any time, there is a standard timing as well for these measurements. So measurement at daily time in morning, we know experiment and class as well. If you are interested to measure the level of water, a hook gauge is used, which is coming from down to upward. So it has more accuracy. So hook is used to measure the water level in this pan. So it is basically first pan which is used, that is USBR, United States Bureau of Reclamation Class A pan. So it has the standard condition to measure the evaporation. Second is ISI standard pan evaporimeter for India. It is also called Class A pan. This is made of 0.9 mm thickness copper sheet. This is copper sheet. Tinned inside, tin painted or tin condition is developed inside, and outside it is painted white basically. A fixed point gauge here you can see indicate the level of water we are measuring here, and everyday water is added. Measurement is taken at the same time every day. It is also placed 15 centimeter above the soil surface in a wooden platform so that disturbances are avoided. This is the mesh which is used standard to cover animal or bird are not affecting the level or amount of water in this tank, in this pan. And that pan is basically used to measure the ET, which is connected later on to evapotranspiration. Now, third pan is sunken screen pan. We have made of unpainted galvanized iron sheet, 920 mm square and 460 mm deep, basically this inner ring, buried into soil or ground within 100 millimeter of the top. This has advantage like it is resembling the condition of actual field condition. These previous two pans are placed on platform. Here is exactly inside. So it this is aerodynamic in this particular area. However, its disadvantage, it is difficult to detect any leakage if there. Extra care is needed to keep the area free and that is idea. But it is sunken pan, that is the pan we are using to find out evaporation from the area. Fourth is US Geological Floating Pan Evaporimeter. So there is in water body, from the water body to find out evaporation, just like from a lake, pond, there is a floating kind of pan to simulate the characteristics of large water body of losing water as evaporation. Of 900 millimeters height and 450 millimeter depth condition deep, and supported by drum floats in the lake so that it is floated and amount it is measured every time. So what are the disadvantages? Is a high installation cost and difficulty in maintenance because it's in sometimes disturbed from the lake condition in the. However, these are used to measure the evaporation from different conditions, from the field, from the surrounding condition by using a raised platform pan, and here it is in one pan condition. Now, it's important. From these, we are simply estimating first its ET0, that is the reference evapotranspiration. There are two terms, ET0 and PET, potential evapotranspiration. So ET0 is basically the reference evapotranspiration or a crop which is taken as reference So ET0 is simply estimated pan evaporations or evaporation that is measured in these pans, that is used to estimate the ET0, that is reference crop evapotranspiration, as evaporation from the pan multiplied by the pan coefficient. So in this way, pan coefficient depends on the location of surrounding ground cover, distance of place of the measurement from we are measuring at center at the relative wind at particular. So, yes, pan coefficient is of the area and instrument or the system or the span itself to find out reference evapotranspiration, pan evaporation that is measured. Now, evaporation as an indicator of crop ET we are using. So, difference between then information and like non-similar what is coming, it has a different zone in the area, it will have more radiation. Second, it could be a difference like wind profile over the crop differ from that over side as it has a different it is any absorption more than radiation. However, it has a difference than the actual crop. So it's basically heat storage in pan may be considerable and will contribute to more evaporation than the actual evaporation from the area. So evaporation continues in night, right? If night time do not evaporate and the night vision wave is closed and there is a dark condition or there is no evaporation. No resistance here. It's ETC. ET crop is KP, pan coefficient, right, into pan evaporation. So here ET crop is simply pan coefficient, crop coefficient into its a pan evaporation. So we can have the idea. Sorry. It is correct here. I'm mistakenly wrong. It is giving you here information about reference crop, and here we are getting actual crop. So reference crop is multiplied by the pan coefficient and pan evaporation, and actual crop is we are getting by actual evaporation or pan evaporation multiplied by the crop coefficient. So there are two coefficients, crop coefficient and pan coefficient. So here in this way we can find out or we can estimate the ET, that is either actual, that is crop ET, or it is potential, that is reference condition evapotranspiration. Now the third well to find it was Lysimeter, field instrument thought, those were the measurement aspect. It was pan evaporation or evaporation based estimation. So pan based evaporation kind of measurement. Solar energy that is coming, here you can see, to calories per square centimeter per minute. That is a kind of solar constant that is above the atmosphere. Earth's surface, we have atmosphere. So above the atmosphere, it is calorie per minute per square centimeter. It is coming. That is solar. However, once atmosphere comes into or it is scattered and portion, it is coming on the. So for different condition, we can find valence is used by the system. And you know that it is calorie here we have used, but it is 50 calories per gram of water we evaporate from water or plant surface. Then we can make a kind of energy balance approach to find out how much water is lost from the system as evaporation and transpiration. So combined it is called evapotranspiration. It is same, it is written vaporization is 540 calorie per gram and is vapor flux. So in this mass balance, I am not going into detail, but simply understand that it's energy balance we can use to find out evapotranspiration of a particular crop in a particular area. So energy balance approach, the equation can be applied over any time period, just like it is different methods of measurement we have seen. It is either from daily or it is seasonal or for a small plot or a basin. But this particular method can be used for any time period. Unit of the terms are calories per centimeter square per minute because it's energy. So 1 calorie per centimeter square per minute is simply 1 millimeter of water that is evaporated per hour. That is equivalent to. And the amount of radiation energy available on the horizontal land surface is simply known as net radiation. So energy incoming minus outgoing, that is the simple balance after that is absorbed by the different condition of maybe the cloud, just like here, which is absorbed, which is reflected back. So this is giving you, or simply we can make the energy balance. So in that sense, we can use the energy balance approach finally to find out the amount of water that is lost because of the available energy from the source. So this is the third approach. So measurement by lysimeter, energy balance approach, that is. Third is pan evaporation, that is used to estimate actual and potential evapotranspiration. And fourth one is climatic approach or climatological approach. What is climate? I told there are 5 basic components of climate: temperature, precipitation, solar radiation, wind speed, and atmospheric pressure. So these information or either of these information we are simply using to find out how much water it will get removed from the system. So climatological approach is simply in that way, and most of the approaches are using temperature, except a very refined condition that was developed by FAO, Food and Agricultural Organization, by 2 scientists, Blaney and Cradle, in 56. So they have FAO 56 method that has almost all atmospheric condition: wind condition, resistance condition, atmospheric pressure condition, vapor pressure condition, and so on. So just like for an example, let us start from here. Blaney Cradle method. It gives us an idea about conjunctive use, that is theoretically little more than ET. So ET, conjunctive use of water by the crop in inches, that was Vlanik-Riddle first given this idea, for a given period, maybe for a particular year, particular season. That is K, that is empirical coefficient, and T is the mean temperature in degree Fahrenheit. It was developed for US, and that's why it's taken temperature in Fahrenheit. Conjunctive use of water in centimeter rather than millimeter, and temperature in degree Celsius. But later on, we got the refined method where we can use the units like degree Celsius, meter, and so on. So it's a simple idea of empirical coefficient, that is for area or characteristics of area. P is basically percentage of daytime hour of the year, that is basically sunshine, and T is the temperature in degree Fahrenheit. So percentage of daytime hour of the year which is having sunshine, we can simply estimate possible sunshine hour for the particular month, just like it is well defined for a latitude longitude condition, and possible hour for the whole year. Possible, both are the possibility. There is no consideration of cloud cover because sunshine hour is getting affected due to cloud cover condition. So in that way, this gives the simple idea about conjunctive use of water by the crop in inches. We have empirical coefficient K, and this is to make year condition, like season has 4 months. So it is summation of all 4 months from 1 to 4. So P is your percentage of day hour time, that is sunshine hour, with respect to whole year, and T is the temperature in Fahrenheit. Now, this was developed to fit arid condition. Now, this is more suitable. Vlanik-Riddle method is more suitable for arid condition because this was developed to fit in arid condition climate and will give satisfactory estimate water required. Arid condition, seasonal. It is not working well for daily condition. Second method, that is empirical approach to estimate the evapotranspiration after Vlanik-Riddle. It is Thornthwaite method. It gives you an idea about potential evapotranspiration. What could be the maximum evapotranspiration? That is potential evapotranspiration with respect to atmospheric condition, and reference it is with the crop condition. So potential evapotranspiration that was given by Thornthwaite, this idea or method, is simply 16 times 10 your mean monthly temperature, and I is heat index, that is I capital is heat index for annual condition, that is summation of all 12 months, that is summation of all 12 months, smaller I here. Monthly heat index is simply temperature, that is mean monthly temperature divided by 5 to the power 1.541. This is empirical relation, has no explanation why it is happening like this. So Thornthwaite developed the empirical relation to find out potential evapotranspiration for a particular season, or here it is for the whole year condition, to divide into months. So in that sense, Vlanik-Riddle, Thornthwaite, and then it is most important, the third I am telling you here, but there are number of other methods you can find out, but these are few more important. I am listing here or giving you an idea how are they working. So third one is FAO, Food and Agricultural Organization 56, in year 56, 1956, Penman and Montieth, two scientists, gave this idea to estimate the reference crop eating. So FAO 56 Penman equation is grass reference, grass it is used. Equation that was derived from the ASCE, American Society of Civil Engineers equations, by fixing grass height. There must be some standard reference crop, reference grass. So alfalfa was taken as a reference grass of height 12 centimeter or 0.12 meter. That is fully grown in that sense. It is covering the whole area uniformly. It is covered. Our land surface is covered uniformly by the grass. Assuming measurement height of any condition or atmospheric variable or climatic variable 2 meter above the land surface. You have learned this. Why 2 meter? Because of to avoid any resistance or any influencing condition that occurs on the soil surface. So measurement of atmospheric variable are taken place at 2 meter height from the land surface. So assuming measurement height of wind at 2 meter, measurement height of psychrometric condition at 2 meter, and latent heat of vaporization is taken here in this particular condition 2.45 megajoule per kg of. So in that sense, FAO 56 Penman Montieth is simply trying to find out the energy that is available at the surface by taking the information or measurement at 2 meter without any reference for a reference crop of alfalfa having height of 12 centimeter that offers the same level of resistance. If you recall, 70 seconds per meter, what we were discussing just now, bulk surface resistance of this crop, that is 12 centimeter high. Alfalfa is the grass that is grown, and it offers or develops a resistance to blowing wind as particular speed, that is 70 seconds per minute. So result is an equation by this Penman and Montieth condition that defines the reference evapotranspiration. What is reference? That is alfalfa grass. From a hypothetical grass surface having fixed height of 12 centimeter, bulk resistance that is offering is same 70, and that is another condition as well. Reflectance of this solar radiation, that is 0.23, albedo that is called. And by using this condition, it was used to develop RFAO 56 Penman Montieth, more reliable, more precise it is called. It is simply given in this equation. ET0 is, this is developed equation 0.408 delta radiation G and so on. So these terms are described here. ET0 is a reference evapotranspiration, that is in millimeter per day. The beauty of this equation is it is working on daily time step. Rn is your net radiation at the crop surface, that is megajoule per meter square per day. G is soil heat flux density, that is megajoule per meter square per day. G here. T is the mean daily air temperature at 2 meter height. It is measured in degrees Celsius. These two, U2 is wind speed that has been measured at 2 meter height from the land surface. Here ES and EA, that is saturated vapor pressure and actual vapor pressure of the air at that condition or temperature condition. So saturated vapor pressure deficit, it will be saturated minus actual will be a kind of deficit that is measured in kilopascal. And this delta in equation here, it is basically the slope vapor pressure curve that is measured in kilopascal per degree Celsius. And this gamma is basically here is psychometric constant that is in same unit kilopascal per degree Celsius. And in this sense, we can find out what is reference crop evapotranspiration at that particular temperature and other conditions. So it's most reliable estimate of it is tested for different conditions. Now, if we have this, we have measured by using lysimeter, field experiment and other condition, that is measurement. There is no correction. It's basic method. It's measured evapotranspiration. Second, we measured evaporation from the fan, and we are simply trying to find out crop ET. So we need to multiply. Suppose that is ETC, that is crop, is simply Kc into that is crop coefficient into fan evaporation from the fan. So it is one coefficient. So how to find out one coefficient? That is important aspect now. It is basically the crop coefficient approach here. Now, what is crop coefficient? To get the ET, actual ET for a particular crop, to get the actual ET for a particular crop, here we have measured either evaporation or evapotranspiration, that is reference for the reference crop condition. We need to find out for a particular crop to get actual simple crop multiplied coefficient that is for particular crop. This is crop for this for a that is simply multiplier of crop coefficient to reference evapotranspiration, that is crop of it's showing a bad network. Yogesh, Shruti, Naveen. I was audible or not, Naveen?
Sir, it is audible.
Okay. Because I'm not getting any response, so I'm thinking whether you are there or I'm disconnected and simply talking in air. So it is clear, crop coefficient, it is basically the crop coefficient which is used to get the actual crop ET from the potential crop ET or reference crop ET. Sorry, reference crop ET is reference evapotranspiration that is developed for a particular reference crop. If we multiply it by the crop area, we can get that crop ET, that area. So crop coefficients, coefficient Kc is affected by crop characteristics. Which crop? Sowing stage of the crop development, means it is whether sowing time, it is germination time, it is developing time, it is mature time, it is time. So it is basically the multiplier. Reason being, ET will be different at different time. So this Kc is depending on crop characteristic, which crop, which growing stage, and what climatic condition. right? So climatic condition, that is including frequency of rain or irrigation. So initial stage, say simply germination and early growth stage condition, crop development condition, just like end of initial stage to attain of effective full ground cover, and that is leading towards the maturity of the crop. So KC, we are talking about different crop growth stages for the KC condition. Then mid-season stage, crop development stage to start of maturity now, and late season or late season stage KC value that we can find out for the mid-season stage until full maturity or before harvest of the crop. So there are different KC values for different crop growth stages or different crop stages. If we know those KC values for a single crop for all the stages, we can find out ET for those stages to find out the total water requirement by the crop in the whole cropping period. Now, there is a simple pictorial representation of this KC, just like it's a KC initial time here, initial KC, right? So it's a crop coefficient here. We have simply for this particular period, 20% period of, this is just a hypothetical case, 20% period of its whole season, crop season. It is initial condition where crop coefficient is very less. Suppose here it is near about how much? 0.25. So if we have estimation of ET0 here multiplied by 0.25, that will be actual crop ET for this initial stage. Second stage is development of the crop. So crop development stage, that is from beginning to here, it is 50% time of the total crop period, or it is 30% time of the 30% period in between from initial to mid. So in that it was for beginning and now it is for ending condition. So in somewhere we can find out what will be the value of crop coefficient. Then it is mid-season stage where we have from the beginning, from the starting of the crop here, it is 70% of the time, or it is 20, then 30, and 25% of the time. Mid-season, it is late where crop mature last, making 100% of the crop growth period. So we need to find out what is the crop coefficient for different stages of crop growth in this season. So it's called the general trend of KC, crop coefficient, at different crop stages. Now there are two terms, crop ET, that ETC, ET, crop, and that is reference ET. How they are differing. That's why we need multiply here KC to find out this value. So ET, that is represented in or presented in inch per day, and it is for different months. We can assume here a kind of season, crop season. So reference ET is always higher. Reason being it is one reference. Alfalfa grass is a reference grass, which is having a certain growth characteristic. There is no limitation of water to get supplied to the alfalfa crop, right? With respect to that, any other crop, we are now trying to find out evapotranspiration. So KC is always more in all stages. ET0, that is reference ET is always more. And now it is matter of KC. To develop, find out crop evapotranspiration. So it's basically the kind of comparison of ETC and ET0. So ET0 is always more usually for most of the crop than ETC. Now Factors influencing the crop coefficient, because we are estimating crop coefficient for different stages. So what are different factors which are influencing crop coefficient? It is basically the crop type. It is basically the climate. It is arid, humid, which particular climate condition. So KC depends on crop climate type, soil evaporation, and crop growth stage. It is very clear here. Different crop growth stages, KC is different. So it's KC is influenced because of crop type, climate, soil evaporation, and crop growth stages. It represents the integrated value of four major factors. In that sense, KC represents four integrated conditions or factors, which are basically crop height, that influence this resistance or aerodynamic resistance, albedo, that is reflectance, canopy resistance, and evaporation from the exposed soil. So if it is the initial or beginning of crop, soil is exposed more. So there is a strong component of evaporation, less component of transpiration. But when the same crop is grown, it has no free surface or soil surface is covered from these leaves. So here is suppressed and transpiration is increased. So in both the condition, evaporation plus transpiration is equal to the here evaporation plus transpiration when the stage is changed. So evaporation from the exposed soil, it is important. So also these four factors, crop height, albedo, canopy resistance, evaporation from the exposed soil, these characteristics distinguish a crop from a reference grass, that is alfalfa, and grown up to 12 centimeter in height, offering a resistance of 70 seconds per meter and has a albedo condition of 0.23. That is reflectance, that is 0.23. So now these are the factors influencing KC. So you have learned what is ET, what is evaporation fan. We are simply multiplying by the KC to find out the ETC, or it is reference crop ET, that is ET0. We multiply by KC to find out ETC, that is ET crop. Now determination of crop coefficient KC, it is important task. Now you have seen that it is varying or it is changing with respect to crop growth. So determination of crop coefficient KC for the crop is determined experimentally only. We need to experiment in the field. Where? In lysimeters. If we have measured ETC of the crop and we know that it is potential ET0, we have measured this ETC in the lysimeter, suppose a lysimeter, we can estimate back what is the KC, right? We know the ET0, we measured ETC, we can find out KC. Why we are doing this? We are doing this so that in places where we do not have these facility, we simply use the KC value and multiply it with ET0, that is reference crop ET, to find out actual crop ET. So KC for a crop is determined experimentally and relates the physiology of the crop, the degree of crop cover, the location where data were collected, and the method that is used to compute reference crop ET0. KC value or values are affected by relative humidity in the atmosphere, wind speed, and time of basically sowing or initiating the crop condition. It varies during the season. So it's different season because it's a time, it's a season, I've already seen it. So Kc varies during the season. Now crop evapotranspiration under non-standard condition, that is ETC is adjusted. It is basically the condition when there is cloud, graph reference, just like climate, radiation, temperature, wind speed. We are simply using graph reference graph, well watered graph, that is simply multiplied condition to get the reference evapotranspiration. We have this condition, that is reference evapotranspiration. We are simply multiplying the crop coefficient or crop factor to get the a kind of adjustment from the crop grown under management and from ETC is equal to simply Kc into ET0. Here. But if there are certain management conditions which differ the characteristic of ET0, where ET0 has been taken or measured, and we have the crop, we are simply adjusting for any other condition, just like this measurement has been taken place in arid region, and we want to use this condition for a humid condition. So we need to adjust this crop ETC, that is called adjusted condition, with this ET0 which has measured to different properties like water stress or atmospheric variation, that adjust multiplier, that is constant. So what is stress coefficient? It is called just for one condition, humid, water stress, or any other condition which is basically adjusted because of a certain characteristics of the growing condition. So now general selection criteria for simple and doer crop, you can have, I am just giving you an idea, it is beyond your scope, but suppose it's a mixed crop like corn, or it is a single crop with the only crop which is grown in the area. But you might have seen in wheat fields, there is another mixed crop as well, maybe gram, maybe lentils, maybe mustard that is grown. So there are crops and double crop. So we are simply getting the crop coefficient because it's a matter of irrigation. It's not the crop individual, but it is in a combination in the same field. We need to find out the combined Kc value, crop coefficient. So single crop coefficient versus multiple crop or double crop coefficient. So effect of crop transpiration and soil evaporation are combined into single crop coefficient. That is very well known condition. We are simply revising it. The crop coefficient or coefficient coefficient integrates differences in soil evaporation and crop transpiration rate between the crop and the graph's reference surface. Means it is used to multiply with ET0, that is a reference graph condition. So this is simply Kc, which is trying to manage this condition of alfalfa grass with respect to the actual crop, that is giving you ETC. So single crop coefficient expresses only the time averaged, maybe multi-days effect of crop evapotranspiration, used to compute ETC, that is actual crop transpiration for weekly or longer time period, and the time averaged single Kc is used for planting studies or crop studies and irrigation system designed where the average effect of soil wetting and acceptable and relevance such as surface irrigation and say sprinkler system irrigation condition. Now it is a dual crop coefficient that is important for us. So effect of crop transpiration and soil evaporation are determined separately. Two coefficients are used, the vessel crop coefficient, that is crop coefficient KCV for vessel, to describe plant transpiration, and the soil water evaporation coefficient, that is KE, to describe evaporation from the soil surface. So crop coefficient in that case is vessel crop coefficient plus evaporation coefficient, that is KE. In that sense, KCB, that is vessel crop coefficient, is the ratio of ETC, that is actual crop evapotranspiration, to ET0, that is reference crop evapotranspiration when the soil surface layer is dry, but where the average soil water content of the root zone is adequate to sustain full plant transpiration condition. And KCB, that is here, that is vessel crop coefficient, represents the baseline potential KC in the absence of the additional effect of soil wetting by irrigation or maybe precipitation. So it's a detailed theory, and we need to simple learn that it is single crop coefficient or it is a dual crop coefficient, and in that sense it is again adjusted. What you have seen for single, KC initial, mid and end season for a single, and this is for dual condition to find out the KC for the single condition from there. Factors influencing ET evapotranspiration, that is meteorological factors like solar radiation, relative short wave radiation, sunshine duration, albedo, net solar radiation, long wave radiation, soil heat flux, means parameters which are given there in FAO 56 Penman-Montieth equation at least. So those are the meteorological factors influencing the evapotranspiration: air temperature, humidity, vapor pressure, dew point, radiative, relative humidity. Those are affecting the atmospheric moisture content. So these are the factors related to meteorology which are influencing the evapotranspiration. Second is the crop factors. So first is the meteorological factor, crop factor, management factor and management environment condition, which are basically affecting the evapotranspiration. So what are the crop factors affecting evapotranspiration? Crop type, crop variety, crop development stage. Third is management, soil salinity or soil properties, land fertility, application of fertilizers that increases permeable soil horizon below the root zone. It is not allowing groundwater to get contributed, or it is not allowing water to go for deep percolation. It is creating different kind of environment. So presence of hard impermeable soil horizon below the root zone. Disease and pest means that affects the health of the plants, that affects the loss of water, that is ET. Poor soil management, it is means no drain condition, or it is most of the time flooding situation there. So poor soil management and soil water content, whether it is at field capacity, it is building point, that also depends the loss of water from the area in of evapotranspiration. So there are three conditions: meteorology, or atmospheric properties, crop characteristics, and management conditions, which are affecting or influencing the evapotranspiration of any particular area and crop. This is what you have next class as well. Let me finish here, and next we will talk about irrigation efficiency, and then later on different methods of irrigation. My idea. Anybody, any query if you have? Because I'm not I don't think that everybody is present here even.
Sir.
Anybody want to say something? Naveen? Yeah. Yes.
Sir, no queries.
No query. Okay. Then you may have another class. Please go there, and we will meet tomorrow again. And there will be one test on Monday from 10 to 11. I will update the learning up to the previous class, that was water conveyance, I think. But to that, we will have that test. Okay?
Yes.
So have a break from this class, go to another class, and we will meet tomorrow again from 10 to 11. Okay, see you.
Thank you. Thank you, sir.
Okay,
Thank you,
welcome.
sir.
Thank you, sir.
Welcome, welcome.